Okay, seminar sheet 7, question 1 was asking you to remember what the architecture or the network design would look like for the Bainbridge oscillator. So let's start off with the basics. We need our operational amplifier. In our operational amplifier we're going to have our feedback system. Okay, looking something like that. So that's our negative gain. Now we need to think about what our positive feedback fraction is going to look like. Our positive terminal has a resistor and a capacitor down to ground, and also it has a resistor and a capacitor in series to the output. RC, RC. Effectively we therefore have a parallel component, which is here. We could call that ZP, and here a series component, ZS. Let's have a look at what those equations would look like. ZS is equal to R plus 1 over J omega C. Okay, that's the reactance of the capacitor and the resistance of that resistor. We may want to tidy that up at a later date. Let's have a look at ZP, the parallel resistance. ZP is effectively R in parallel with C. So we've got, let's just use the product over sum rule, R divided by J omega C, all divided by, that's the product. Now we need the sum, 1 over J omega C. Well, that's a little bit messy. Why don't we multiply the numerator and denominator by J omega C, and we will clean up ZP. We're now left with R divided by J omega CR plus 1. Okay, I think that's an awful lot easier expression for ZP than the one above it. ZS, okay, is not bad. It's probably as good as you can get at the moment. What we really want to do now, we've got those two expressions, is try and calculate the value of the feedback fraction. Let's call this node here VA and this node VB. So this is the signal feeding in. We want to know what VB divided by V out actually looks like, which is an expression for this feedback term. In effect, we're trying to look at what the Barkhausen criteria will be. Okay, so I'll do that on another slide. Okay, nice clean slide ready to go. So what we need to do now, we're going to be calculating quite a bit of maths. So let's just refresh our memory as to ZS. ZS is equal to R plus 1 over J omega C, and ZP in its nice simple form is R over J omega CR plus 1. Okay, now if we calculate, or if we look at that VB divided by V out, it basically was a voltage divider expression, so it'll resolve round to ZP over ZP plus ZS. Okay? What we now want to do is to substitute those two values, or those two expressions, into that equation, and then do an awful lot of mathematical simplification. So let's start. R over J omega CR plus 1, all divided by R over J omega CR plus 1. Okay, there's my ZP term. Now I'm adding in ZS. Oh, sorry, there's no R there. Got carried away. So there's our expression. What we need to do now is we need to simplify it because this is too damn complicated. The easiest thing to do here is to spot this denominator here. If we multiply by this whole term, we should be able to simplify the numerator and simplify the denominator. So let's try that. R over j omega CR plus 1 multiplied by that denominator becomes R. This term multiplied by that denominator becomes R. This is this R multiplied by this denominator, j omega CR plus 1, plus 1 over j omega C multiplied by j omega CR. So let's do that one. J omega CR plus 1. That's my multiplication factor, all divided by j omega CR. Okay? Now what we need to do is we need to simplify and figure out what's going on. Well, if we notice we've got R and R's here, we could start to cancel through by R's. We also need to cancel through by this j omega CR term. I've done it again. Sorry, there is no R there. That's j omega C, and that's this term here, j omega C. So, what have we got now? Let's take out our R's and cancel them, so that becomes 1, 1, 1. Here we have j omega CR and 1 and j omega C. So if we're dividing through by R, we can put an R in place there, okay? Because we're dividing through by R. This term and this term cancel, and we're left with 1 over j omega CR, okay? Okay, from here. So let's just tidy all that lot up. Our expression now looks like this. 1 over 1 plus 1 plus j omega CR plus 1 plus 1 over j omega CR. Simplify, collect up all the 3's, we're left with 1 over 3 plus j omega CR plus 1 over j omega CR. Again, one little simplification that we can do, because we've got j and j in the same terms here, we can simplify that. I'll just put it up here. We're left with VB over V out is equal to 1 over 3 plus j into omega CR, and because the j was in the denominator, not the numerator, we have the minus 1 creeping in, 1 over omega CR. Okay, and that is the expression that you were deriving for. Okay, so there's our fundamental feedback for the Barkhausen criteria. We now have a real part and an imaginary part. The imaginary part will equal 0 at a break frequency, which will therefore be proportional to the break frequency, and we have the real part, which is effectively going to show the magnitude. You know, how much signal is fed back and what does our gain need to be to establish oscillations. Okay.